Welcome mechanics students. I'm here to tell you that mechanics is number one. No matter if you like it, I'll tell you to sit down and write it because mechanics is number one. Alright, well hopefully you recognize that song. It's by Nelly and I just love Nelly's music and thought I would wear my St. Louis t-shirt to represent Nelly and his hometown. If you ever get a chance to visit St. Louis, there's an awesome steel arch there, so you can even apply your mechanics materials knowledge. When you're looking at the arch, you can think about the forces and the stresses that's going on in such a beautiful structure, right? I hope you know who Nelly is. One of the things is as I get older, you guys stay the same age, and one of these days I'm going to come to class and you're probably not going to know who Nelly is, and it's going to just break my heart. But if you do know who Nelly is, I hope you'll come take a ride with me to read some LOs at the side of the class with me. Why would you want to leave? Hey, it must be mechanics, right? So these are our learning objectives for today. We want to apply the force method to solve some engineering problems. Then we want to define a material law relationship for metals, for temperature effects, and then we're going to explain stress concentrations and solve some engineering problems. To get started, I just want to review what we talked about the last class when we talked about the force method. So you'll have to excuse my country grammar there, but I want to tell you about the force method. In the force method, right, we have what we said was an indeterminate structure or an indeterminate system. And we said it was indeterminate because in this case, we can't clearly define what the reaction at point D and the reaction at point A is because we only have one equation of equilibrium, but we have two unknowns. So we said using the force method, we could use a superposition of two problems that we do know the answers to. So in this case, we take this system and we're going to say that the results of this system are equal to two systems that look like this. And so we basically remove the support at D and we say, okay, well, we're going to apply the force P at point C. And what will happen to this system? Well, this system will stretch, right? So this system is going to shift to the right. So it'll move some distance over. And this bar moves over a little bit too. And we can calculate this deflection. And I'm going to calculate this deflection and I'll call it delta P, or the deflection or the extension due to the load P. Now, this isn't really accurate because we can't just remove the support and not have it in our problem. So we have to somehow incorporate the support. Well, what does the support do? The support provides a reaction. So in my second part of this superposition, I'm going to apply a reaction force, in this case at point D. So I know that the wall at D would really react on this bar and push it back. What will happen in this system? Well, in this system, we'll see that it'll compress. And this one will compress as well. And we can measure this deflection to the left, and we'll call this delta due to the reaction dx. All right, so I now have two problems that I can easily calculate delta P and delta dx. So these are not statically indeterminate. I have means of calculating both of these. And I can then add these two together to get back to my original deflection. Now, what was my original deflection at point D? Hopefully you said 0, because the bar was in contact at point D. As we see in our example, we're going to have a little bit of a gap here, so delta D could be some real number, some real distance. Now in this case, delta D is 0, but regardless, we'll say that the total deflection at D, delta D, is equal to the deflection due to the load P when I imaginarily remove that wall, plus the deflection backwards due to the support reaction, delta dx. And then this is what we call our compatibility equation. All right, so hopefully that makes sense. Hopefully that clearly describes the force method in your mind. One thing I do want to point out is that delta P here in this example, P is going to come fully back through rod AC, and really rod CD is just along for the ride. So really we're looking at stretch only in member AC in this particular example, whereas the reaction dx affects both segments CD and AC. So we would have to calculate deflections. Delta dx is going to be dependent upon deflections in CD and AC. So hopefully that makes sense to you. If it doesn't, we're going to see it here in this example problem. In our example, we have rod AC that's made of steel and rod CB that is made of brass. There is a gap at the wall between points B and D of 0.2 millimeters. All our other loads and our properties are given, as well as the geometry of the rods. So the first question we ask ourselves is, will the rod contact the wall at point D? Okay, so until the rod contacts the wall at point D, this is a statically determinate problem. All we have is a rod that's fixed at A and a load applied to it. So hopefully you can see that this is, this goes back to our statically determinate problems, and we would be able to solve for the total deflection at point B. I'm going to set this up in terms of our engineering toolbox. Now, our engineering toolbox is always applicable for all cases. So we can do this for statically determinate and indeterminate structures. And then there's just varying levels of complexity in terms of the math and algebra that's required to solve. So if I perform equilibrium on my current situation, I have rod ACB drawn and it's fixed at A. I'll include the geometry here. I've converted the geometry from millimeters to meters just for use in my calculations. All right, so this is our free body diagram of the current situation. Right now, the wall, it has not contacted the wall at point D, so D has no effect on this bar. And because I'm wondering if it makes contact with the wall at D, I want to calculate this deflection under the load P. So I've labeled this delta P, and this is very similar to the delta P that we stated in the opening review of the force method. All right, real quick, I just want to get my diameters in there so that I can kind of move forward with my free body diagram and do my calculations. As we already stated, this is a statically determinate problem. And we can see that if we go ahead and we add our forces, our reactions to this free body diagram. So we see that we have one reaction, a reaction AX at point A, and it would be oriented to the left since the load P is oriented to the right. So I only have one unknown variable, and if I do a sum forces in the x, I would see that I could solve for that value of AX. Associated with equilibrium, I can also come up with an axial force diagram for this rod. We see that all the load P has to make its way back to AX. So if I was to draw a free body diagram of a cut somewhere in AC, I would see that AC is under 300 kilonewtons of tension. However, a cut in BC, somewhere between C and B, would indicate that we have basically zero axial force there because none of that load P is traveling through rod CB. Our second tool in our engineering toolbox is kinematics. In kinematics, we
relate displacements to one another in our structural system. And so we are after calculating delta P. Using a kinematics equation, I could say that delta P is equal to the total deflection at point A plus the deflection of C relative to point A plus the deflection of B relative to point C. And so we saw this as we did statically determinate systems. We kind of add up those deflections along the length, kind of starting at that fixed end. Finally, we use our third tool, our material law, and that says delta of any particular segment equals PL over EA for that particular segment. If you're looking for another way to remember Hooke's law, you can just think that Hooke's law goes like this. Under PL, EA, EA, uh-oh. We can calculate deflection tonight. Under PL, EA, EA, uh-oh. Something like that. All right, so back to our calculations. We want to take our material law and now substitute it into the kinematics. So we're going to go ahead and do that. We see that delta A is going to be 0 because it's a fixed end. So that leaves us that delta P is going to equal PL over EA for segments AC and for segment CB. But because all of the load is in AC only, and we saw from our axial force diagram that there was 0 load in segment CB, then PL over EA for segment CB is going to go to 0 because it has no load or no axial force. So like I said at the beginning, CB is just along for the ride. It doesn't stretch, it doesn't compress. It just kind of shifts to the right as segment AC stretches. So finally, we can do our calculations for delta P. So delta P is going to equal the value of PL over EA for segment AC. And so we can substitute. For the axial force in segment AC, we have 300 kilonewtons, or that's 300,000 newtons. The length of AC is 0.3 meters. The modulus of elasticity for AC, which is steel, is 200 times 10 to the 9th pascals. And the area for segment AC is pi over 4 times the diameter, which is 0.0375 meters squared. All right, again, I've now put all of we have to be careful with units, so I put all of my forces and dimensions in newtons, meters, and pascals, so that when I solve this, I get the answer in terms of meters. So I calculate delta P to be 4.074 times 10 to the negative 4 meters, which is equal to 0.407 millimeters. All right, we'll go ahead and box that answer. Now, the question was, will the rod contact the wall at point D? So if I return back to my problem, I wanted to know, is point B going to hit the wall at point D? So we saw in the initial problem that there is a gap of 0.2 millimeters. Delta P is calculated to be 0.407 millimeters. So because delta P is greater than the gap, we would expect the rod to make contact with the wall at point D. The next part of the problem asks us to calculate the internal forces in each of the segments. So we're asked to come up with the internal force and the internal stress in segments AC and segments CB. Well, now that we know that the rod makes contact with the wall at D, the problem becomes statically indeterminate because now we have support reaction AX and support reaction DX, but we only have the one some forces in the x equation to solve. So we have two unknowns, but only one equation, so it's statically indeterminate. To solve this statically indeterminate problem, we can go through and we can apply the three tools from our engineering toolbox. But we talked about using what we call the force method. So I want to try using the force method here to solve this particular example. All right, so in the force method, I do a superposition of problems that I know, simpler problems that when their results are added together equals the more complex problem. So I'm sketching some free body diagrams here. I need 3 of them across. And so you see that in the free body diagram on the left, this is my actual problem. My actual problem has rod ACB, and it has a wall at A, it has the wall at D, and there's a gap between points B and D. Now I'm going to pretend that the wall is not there. So in my second free body diagram, I pretend the wall is not there, and I basically just remove it from my free body diagram. Okay, I only removed the wall, I didn't remove the force. So in my second free body diagram, I want to include the force at point C. So I want to include the force P that is going to cause this rod to extend. In my third free body diagram, I need to incorporate the reaction somehow. I know that the rod can't just freely extend to the right, and at some point, once it makes contact with the wall, a reaction dx will initiate. That reaction dx will be oriented to the left and will push back on this rod. If I look in terms of deflections, I can expect in my middle free body diagram there that I would have some deflection to the right, which we call delta P. But when I apply the support reaction, the real support reaction that exists in real life, it would cause a deflection to the left of delta dx. And we say that in total, the total amount of deflection that I'm allowed to have at the end of the rod is delta B on my first or original free body diagram. All right, so I hope that mimics or mirrors the example we set up in the force method. So I think when we first talked about the force method, we looked at just a uniform geometry for the rod. Now we're using different materials and different diameters, but it doesn't change the setup for the force method. And whenever we do the force method, we're aiming to come up with what we call the compatibility equation. And so in this case, our compatibility equation says that the total deflection, delta B, has to equal the sum of the two other deflections, delta P plus delta dx. Now, I've drawn in arrows on each of these deltas. So delta B is to the right, delta P is to the right, and delta dx is to the left. So I'm expecting delta B to be a positive number, delta P to be a positive number, and then delta dx will be a negative number indicating contraction. So the combined delta P plus delta dx has to bring us back to the end of the wall, but we have that gap to account for, so delta B will account for the gap. So delta B is going to equal that distance, that gap distance of 0.2 millimeters or 0.0002 meters. Or 2 times 10 to the negative 4 meters if you would rather use scientific notation. Delta P we calculated in part A. And from part A, we calculated delta P to be 0.407 millimeters. Or 4.074 times 10 to the minus 4 meters. All right, so that just leaves us with coming up with a value for delta dx. Once we do solve for delta dx, we'll be able to figure out how much the support reaction dx is applying to the rod. Alright, so how do we solve for delta dx? Well, if I just gave you the right-hand free body diagram, you would tell me that that is statically determinate and that dx causes basically compression in both members AC and CB. And so that's how we're going to go ahead and solve this. I'll write my kinematics condition for delta dx. Delta dx is going to be, once again, the total sum of the deflections across the entire rod. So that'll be delta A due to the load dx plus delta C relative to A due to the load dx plus delta B relative to C due to the load dx. All right, delta A is 0 because it's a fixed end. And so now I just have to account for what's happening on rods AC and rods CB. Like I already stated, you would tell me if you just looked at the free body diagram for the rod with the reaction force, the one furthest to the right, that dx causes compression in both segments. I could go through and I could draw an axial force diagram for this problem. If you need to see that, go ahead and do it by all means. But I think we can see that one reaction force causes compression in both of the segments. And so it's important that I capture both segments. Both segments AC and CB will be compressing here, and I have to capture those deflections when I do my calculations. I'll substitute my material law for my delta. So again, delta equals PL over EA. So I've substituted material law into my kinematics equation. And now I'm going to write an expression that's all in terms of dx. Because dx causes compression, I'll represent it with a negative sign. So we have negative dx times the length, 0.3 meters. This is for segment AC. AC is steel, which is modulus of elasticity of 200 times 10 to the 9th pascals. And then we divide by the area, pi over 4 times 0.0375 meters squared. And that will give us the deflection, the total deflection on segment AC. To that, we add this deflection on segment BC, or CB. This, again, has a compressive force of negative dx. It has a length of 0.6 meters. It's made of brass, so the modulus of elasticity is 100 times 10 to the 9th pascals times the area in the denominator there. The area will be pi over 4 times 0.05 meters squared. All right, so that's a lot of numbers, but don't be scared by the algebra. We can now solve for delta dx in terms of the reaction dx. And so if we go ahead and solve that, we will get that delta dx equals a negative 4.41392 times 10 to the minus 9th times dx. It's important here that we keep a lot of the decimal places, especially, and use our scientific notation, because dx is a very large number, and then the number in parentheses is very small, so we need to keep enough decimals to maintain accuracy for the deflection dx. Once I have this value, I can then plug this back into my compatibility equation. So my compatibility equation says delta B, which was 0.0002 meters, equals delta P, which was 4.074 times 10 to the minus 4 meters, plus delta dx, which is negative 4.41392 times 10 to the minus 9 times dx. The only variable I don't know is dx, so I'm just going to go through and I'll solve for dx. We find that dx equals 46.988 kilonewtons. It's a positive number, meaning that the orientation that we drew dx to the left is correct. And there we have our answer for our reaction force. Alright, I hope you're following along. If you're not following along, please feel free to reach out to me via email or via GroupMe, or meet me at my office hours. the final step here is to then figure out what the reaction at A is, and then figure out what the forces in the members and the stresses are in these members. So doing our equilibrium, we find that AX will have to be 253.012 kilonewtons, also oriented to the left. Finally, we can come up with our axial forces and axial stresses in each of the segments. For segment CB, we see that we are in compression with a value of the reaction dx. So P, our axial force in segment CB, will equal negative 46.988 kilonewtons compression. And in segment AC, we see that AC is in tension with a value of 253.012 kilonewtons. Stress is just axial force P divided by area. So P over A, our equation for axial stress. So the axial stress in segment CB will compute to be 23.93 megapascals, negative because it's in compression. And our axial stress in segment AC computes to 229.08 megapascals. We can compare these values back to the yield stress for both materials. We see that for the brass segment CB, the brass yield stress is around 80 megapascals, and the steel yield stress is around 350 megapascals. So we see that both of them fall below the yield stress, and so we wouldn't expect yielding to occur in this particular member. That successfully concludes our example problem in which we applied the force method to solve a statically indeterminate system. Woohoo, we're done! So I hope you were able to follow along and you could see the value of using the force method. In fact, as we even move on into our next courses in Structural Analysis 1, if you're in the civil engineering program, you'll see that we'll use a variation of the force method when solving for the reactions in statically indeterminate beams. That's it for this topic. Now we gotta head on to temperature effects.